Um, any questions before we start? Any issues? Let me talk about the schedule for a second before doing anything else. Looking back at the calendar that I handed out. First of all, as I noticed these two guys last time were making faster progress than was on the calendar. Why are we doing this? I think probably partly because I'm teaching out of this book for the second time. Last was the first. In any case, I set aside three class periods for Chapter 2, and we did it in 2 class periods. And I set aside 2 class periods for Chapter, was it 5 was the monotonic? And I just took 1. There really wasn't more there than 1. I don't think we sped through it. So that puts us really 1 week ahead of the schedule. So today we're going to start Chapter 6, I guess it is, on diatomics. And we're going to force that to take 2 periods. And so that'll be today and Tuesday. So then on Tuesday is the 25th of September. So on Thursday the 27th, that's next Thursday, we'll start the next chapter, which is on Chapter 7, which is on classical statistical thermodynamics. I had to take 2 periods on that, and that would be the Thursday the 27th and Tuesday, October 2nd. And then October 4th is a Thursday, and we'll set that aside for review, whatever questions you guys might have. I've learned, I don't think it helps a lot for me to, by way of review, just go through everything. It's more like a time for some back and forth questions or work on problems or whatever. That'll be Thursday the 4th. And then is a long weekend because I'm gone the following Tuesday. On the schedule, I have the midterm then on the following Thursday, which is the 11th of October. Alex reminded me that last time I taught the course I made a take-home midterm. So I haven't decided yet. I'm still thinking about whether it'll be take-home or a midterm on Thursday the 11th. But my thought was that would give you a long weekend to study and review and so forth. So by way of homework, I put up a homework assignment, the second homework assignment on the weekend sometime, or Monday or something, and that's due not today, but a week from today. I think I'm going to add 1 question on Fermi-Dirac statistics, because as I was pondering, I don't think I put a so-called creative one on there, but not a straightforward one. So I want to put a more straightforward one. I'll probably add 1 to it. So that homework's due the 27th. Then I'm going to, on the 27th, give 1 more homework assignment to be due simply a week hence, not 2 weeks, because that will allow you to have had 3 homeworks that you turned in, and at least the solutions are posted before the exam. So you'll then have homework on, so the exam will cover through Chapter 6, through the diatomics. I won't put the classical stuff on it, even though we will deal with it. The reason is that I want the first exam to cover the basics of the approach, the development of what partition functions are, and how they're related to thermodynamic quantities, and the extension to the low temperature case for fermions and bosons, so you see that, as well as Boltzmann statistics. That's a major chunk, and then the monatomic and diatomic gases give appropriate opportunities for applications, and that's enough, I think. And we can leave the classical stuff for, well, it'll be covered in the final, but not in the midterm. I just want to separate it. So that's where we are. Any questions? Sound reasonable?
If the test is in class, are we looking at a test that is for the 1 hour that we have, or?
Oh, that's another good question. We have discovered that there doesn't seem to be anybody in here right afterwards. So I might double check that, and if so, give you a little extra time. Yeah. To be on, well, we've got an hour and 15. I think an hour and a half is probably enough for a midterm. And I think we've got that. Questions? Go. So then, we'll start chapter 6, which is the ideal diatomic gas. So we've actually already done much of the work of the ideal diatomic gas by examining the ideal monatomic gas. We need to develop expressions for the partition function. And once again, we'll assume the temperature is high enough that we can use Boltzmann statistics and don't have to worry about Fermi-Dirac statistics or Bose-Einstein statistics. So we need to evaluate the partition function. So we're going to stay within the realm of Boltzmann statistics. So that the canonical partition function for the system can be written in terms of the molecular partition function, and so we have to think about the molecular partition function. So we're going to make an assumption about the Hamiltonian that we can improve if we want. The basic assumption is that it's separable into a term for translation, a term for the electrons, nuclear term. Now, we already dealt with those for a monatomic gas, and rotation and vibration. To the extent that the Hamiltonian can be separated in this way, the molecular partition function can be written as a product. So we of course dealt with those three terms for the monatomic gas, and it pretty much, what we developed before pretty much holds for the diatomic gas, where the translational portion now applies to the overall translation of our diatomic. So the effective mass then is simply the sum of the little masses for the two particles. That's not new. And there's going to be some electronic wave function, comes out of the electronic Hamiltonian by solving Schrödinger's equation, and there'll be a nuclear portion. Now we'll see later that the nuclear and the rotation cannot always be separated, but usually they can be, to a good approximation. And what else? We know that rotational levels are much more closely spaced than vibrational levels, energy levels, from basic quantum mechanics at the undergraduate level. And to a good approximation, the Hamiltonian for rotation and vibration, those terms are separable, but not exactly. The separation corresponds to the rigid rotator approximation. Here are two atoms, some covalent bond forming a diatomic molecule, and of course this molecule can vibrate and it can also rotate. Now, to the extent that the vibrations are small, it's as if you have a rod of a particular length that's rotating. So the rigid rotor approximation corresponds to being able to separate vibrational from rotational energies. In physical chemistry, you would have seen that that's a good first approximation, but of course, during vibration, the length of the molecule actually varies a little bit, and therefore the moment of inertia varies. And the rotational energy depends on the moment of inertia. So there is some coupling. In this class, in this particular chapter, we're going to neglect that coupling to a large extent. Okay, but you can put it back in. It's not so hard. So if you neglect rotational coupling, then you can write the full molecular partition function in this fashion, and that's kind of what we have to deal with. We've already done that, 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 and we just have to think about these two parts. So, what else might I want to say? Well, just to set us up then, remember that the energy will be equal to it's not correct. Right? So that becomes, in terms of this, right? So the thermodynamic internal energy is written this way in terms of the molecular partition function. It's so the partial of a logarithm with respect to temperature. Well, that's convenient because notice little q is a product, so the logarithm becomes a sum of logarithms. And that means that we will be able to write energy as a sum of translational plus electronic plus nuclear. So to the extent the Hamiltonian is separable, of course, we already do. We can write the energy as a sum, and therefore we can write also the heat capacity. It's a property we look at a lot, which is etc. So we're going to, in the process of looking at these individual Qs, we'll look at the individual rotational and vibrational contributions to the energy and to the constant volume heat capacity. Those are the things we'll focus on. So then, beginning with vibration. This, just to put us in the right framework back into thinking about vibration, which we thought about the undergraduate level in physical chemistry. You can think of the molecule as this two balls in a spring, vibrating like this about some equilibrium bond distance, and there's some energy of stretching, energy of compression. And so there's some potential energy depending on this distance r. I should say this is r, but when so that's a generic curve for the vibrational, for the potential energy as a function of this distance, interatomic distance. So we usually set the zero of energy at RE, and of course near the bottom of the well it's pretty harmonic, but as you stretch sufficiently it won't be harmonic at all. Eventually you break the bond, and of course the smallest r can become 0. Okay, So we usually, the way we think about the potential energies expand in the Taylor series. Etc. And of course, at the minimum, this is 0. And the harmonic approximation corresponds to keeping only this term. And this thing we generally define as K. I'm sorry, nu. Where K is the force constant, not Boltzmann's constant, it's the force constant. Don't get confused all over mu, where mu is the reduced mass. All looks familiar, right? So that's cool, and we know that if we solve Schrödinger's equation for the harmonic oscillator, we get solutions, and the energies are given by this, where h is Planck's constant, and nu is this frequency, and v is the vibrational quantum number, which is an integer 0 or larger. So that's what we have to deal with. So now we can form Q. Sorry. So it's convenient, as it turns out, for mathematical manipulation to factor out the 1/2. So this is what one gets. Well, that's still from 0 to infinity, let's say. And that's where you are. So we want to make this as convenient as we can. But this you recognize is a series that we know. It's a convergent series, and it sums to right? As long as this thing's, as long as, yeah, no, that's the result. So, replacing beta with KT and not confusing this K, which is Boltzmann's constant, with this K, which is the force constant. It's too many representations of K. So that's about it. Now we have a convention. This combination h nu divided by K, Boltzmann's constant, appears very often. What are the units of h nu over K? If you stare at this, what do they have to be? I mean, the exponent's got to be unitless, right? So what does this stuff have to have units of? Temperature, otherwise to cancel this, exactly. So that combination has units of temperature, and it occurs so often we give it its own name. It's called the vibrational temperature. And the symbol is a theta, but it's a capital theta, which I have trouble writing. It looks, when I write it, it looks like an H circled, but it's really a capital theta. So that's the vibrational temperature. It's just h nu divided by K. Now, one thing you'll notice is that the vibrational temperature isn't really a temperature. It's a combination of constants. Okay, it's not like it varies with the real temperature. It's just a combination of constants. Now, why is it? There's several reasons. So we can rewrite this partition function now. Now, you'll see reference to the vibrational temperature fairly frequently in physical chemistry, so it's good to get used to the nomenclature. A couple of points. You know, we evaluated this by replacing it by a sum. We could also have approximated it as an integral if we wanted. Turns out it's usually not a good approximation because the vibrational levels are so widely spaced that they're too discrete. But if we had done that, if we had integrated, not necessarily a good idea, but if we had done that, I won't bother going through this math, we would have gotten KT over h nu, which is T over the vibrational temperature.
Where you circled the U, is that the reduced mass?
Where?
Beta H U.
This? That's an h nu.
H nu.
It's not the reduced mass, it's the
Oh, yeah.
frequency.
Okay.
So it turns out that doing this is a reasonable thing if well, let's put it this way, if the temperature is high enough. So if the temperature is much larger than the vibrational temperature, then replacing the sum with an integral makes sense. You can see that by examining the spacing of the energy levels. So if you take a look on page, let's see, in chapter 6. On page 98 is a list of a few diatomics and their vibrational temperatures. Page 98. Anybody else have? And you can see here the, it's right there. Yeah. For most of those molecules, diatomic molecules, the vibrational temperature is actually higher than room temperature by an order of magnitude for several of them. So this isn't going to work great, for many of them. Okay, so that's that. Now we've got Q vibe, so we can evaluate the vibrational energy. Maybe I should have said, and that's pointed out that for this capital Q, we need Q to the N, which is Q translational to the N, Q electronic to the N, Q nuclear to the N, etc. So when we evaluate the usual thing is, notice we have an N prime in the denominator. Let's do it this way. This is approximate, of course, divided by N prime. So when we evaluate the energies and so when you write the total partition function, we have to think of all these things, and the usual thing is to combine the N prime and the Q translational and treat the other little Q's by themselves. So I'm interested here in the partial of log Q vibe to the N with respect to temperature, so that's what has to be evaluated. And what you get, after you do the math, is this. I think it's fairly obvious where this came from. So this term came from the logarithm of the numerator. There was a minus sign here, but when you take the partial derivative of 1 over t, you get 1 over t squared, so that's canceled out the t squared. Okay, that's where that came from. And I think I left something out here. Oh, oh yeah, and then you have the minus the logarithm of the denominator, so the logarithm of this became here, and so forth. So that's what you get. CV so when you want to calculate the heat capacity, of course you don't have to worry about this term. There's no temperature dependence. You only worry about that term. Let's see. You can see there's going to be that square to the denominator times this. That will give you 4 over t squared. You get a theta here and a theta from up there. and the exponential. So that's then the heat capacity from vibration. Let's think about what it looks like. If you remember back from introductory quantum mechanics and the failures of classical mechanics that led to the development of quantum mechanics, one of those failures was, well, black body radiation, and there were some others, but one was the heat capacity, especially at low temperature, because classical physics was unable to adequately develop a theory of heat capacities at low temperature that matched experiment. Quantum mechanics was. Einstein proposed a formula, and as it turns out, this formula does the trick. Let's see, at low temperature, so if this is Nk, in the limit of high K, large K, this goes to Nk. And you can see that by expanding the exponentials in terms in the series. Right. Let's see if we can think about it. So at very low K, at a very low temperature, at very low temperature, this one should be neglectable, right? So at a low temperature, this becomes right? And this, of course, gets larger and larger as temperature gets small. This gets smaller and smaller as temperature gets small. And the exponential gets smaller much faster than the square, right? So consequently, as temperature goes to 0, this goes to 0. So that is an agreement with this portion of the thing. And to see the other limit, let's see, you'd have to expand and let's go ahead and do it. So now I'm thinking of high T. At high temperature, of course, these are small things. And this becomes so that cancels. And now we just need to think of what the leading term is. So if temperature is getting high enough, the leading term here is the 1, right? And we can neglect all of this. And the leading term here is the theta over t, and we can neglect all of that. So this becomes 1 over theta over t squared, which will cancel this. And sure enough, we then have at high temperature that asymptotic value. So that's interesting, I think, to compare with Einstein's formula for the heat capacity of a crystal. It has a very similar form. 3 Nk, because this is for a crystal. Einstein's formula for a crystal has the 3 degrees of freedom. Here we had only one vibrational degree of freedom, so that's really the origin of the 3 here. Again, there's an NK. I think I wrote that down wrong. Yeah. No key here. Actually, the same kind of temperature dependence here is here, and the same kind of functional form. Okay. And really, this functional form came from the summation, which is the discreteness of the energy levels. So that's vibration. And if I take a step back, what are the sort of most important points? The first is that in the harmonic approximation, you can write down the vibration very simply in this closed form. Don't forget, this is the harmonic approximation, so you can improve upon it. We defined the capital theta, the vibrational temperature, as h nu over k, Boltzmann's constant, and the vibrational energy has sum of terms sort of form, and the vibrational heat capacity has this form that begins at 0 at low temperature and then asymptotically approaches in K. Or if you're talking Avogadro's number of molecules, of course, this is just R. Which is in qualitative agreement with the Einstein formula for a crystal. Any questions? Oh, I guess the last point I'd make, if we think about we know that if you have a large set of molecules, a system with Avogadro's number, each can potentially be in a different vibrational state. So I think it's good for, as we develop our physical intuition, to have a sense for what that population of levels is. So you can, of course, determine that. The population of any particular level will be, go back here, the energy for that level should be and so if you're thinking about some particular molecule, you know what the vibrational frequency is because if you know the force constant, and so you can look at any particular value of V and compare that with the exponential of this stuff with the vibrational partition function. And the book gives a couple of examples, which I think is interesting. Somewhere they had the fractional populations. Well, they have it for bromine, actually. Figure 6-4 on page 98 evaluates this quantity for V, treating V as if it were continuous. And of course, it's not continuous, so you just look at the integral values of V. And this is for bromine, using the force constant for bromine. But bromine's fairly representative, actually. But it's not representative. I think it's got an unusually low vibrational temperature. So what's true of bromine is even more true of other molecules. So you can see that the fractional populational level of the V equals 1 is really quite small. The fractional population of, well, you can see that for V equals 0, this begins at, it looks like about 0.8. So 80% of your molecules are in the ground state, and then it drops off pretty quickly. And bromine has a particularly large fraction of excited states populated, excited vibrational states. Most molecules, it's even less. So really, if you just think about V equals 0 qualitatively, that describes most of your system. That's the point. Gosh, they talk about bromine, and I don't see them give the vibrational temperature for bromine. Well, I would guess it's between iodines and chlorines. So it's probably about 500 K. I can leave that. So then rotation. So we're thinking about rotation of this rigid rod, this rigid rotor. And we saw back, or you saw in quantum mechanics, if you solve Schrödinger's equation for a rigid rotor, I'll just remind you, they're set at discrete energy levels. And where J is the rotational quantum number, and again, it's an integer, 0 or larger. B is the rotational constant. And so it has this form. I, of course, is the moment of inertia. C is the speed of light, and H is Planck's constant. Now there